This topic will look at how to find the shortest distance between two skew lines. It's worth noting at this point that finding the shortest distance between two parallel lines can be done by finding any point on one of the lines and finding its distance to the other line. So the method from the previous topic, the distance from a point to a line, can be used to find the distance between two parallel lines. However, with two skew lines, we need a different method. We're going to consider two skew lines. We want to find the shortest distance between those lines, given that they don't actually meet. If we visualise this as two lines, one along the base of a cuboid and one running along the top of a cuboid, we can see that the shortest distance between the two skew lines is actually a distance perpendicular to both of the original lines. So the red line represents the shortest distance and it's perpendicular to both the top line and the bottom line. We're going to find the shortest distance between the two skew lines given here. We would have already determined that they were skew using methods previously seen earlier in this topic. We're going to consider visually what's going on here. So the two skew lines do not meet, they're in 3 dimensions. The first line has a particular point 4, 2, minus 3, a direction of 0, minus 1, 2. The second line has a point of 6, minus 4, 4, and a direction of 2, 1, minus 4. So these two lines don't meet, but there is a point when they approach each other at its closest distance. We're going to call those 2 points where the lines are at their closest P and Q. So P lies on the first line and Q lies on the second line. Now we know that the vector from P to Q will be perpendicular to both the first line and the second line. So therefore, P to Q, if we were to find the scalar product of it with the direction of either of the two lines, we would get an answer of 0. We're going to find a vector P to Q in terms of mu and lambda. So P to Q can be found by calculating OQ minus OP. Because P lies on the first line, we can write OP in terms of lambda. So 4, 2 minus lambda minus 3 plus 2 lambda. That is coming from the equation of the first line. There. Similarly, we can write OQ in terms of mu. We know that point Q lies on the second line, so therefore we can use the equation of the second line to find an expression for OQ. So therefore PQ will be a combination of these, OQ minus OP, which simplifies down to 2 plus 2 mu minus 6 plus lambda plus mu, 7 minus 2 mu minus 2 lambda minus 4 mu. So as we've previously said, PQ is perpendicular to both of the lines. So if we were to find the scalar products of PQ with the direction of either of the two lines, we would get 0. So this is the scalar product of PQ with the direction vector of the first line. We're going to expand that, set it equal to 0, and we get an expression involving lambda and mu. We're then going to take the direction of the second line, again find the scalar product with PQ, set it equal to 0, and this will simplify down to also give us an expression for lambda and mu. So although the algebra involved in this can be quite tricky, we will end up with 2 equations that both involve lambda and mu, and these are just simultaneous equations. These can be solved to find lambda and mu. So we find lambda and mu from these 2 equations. We get lambda is 6.25, mu is minus 1.25. So therefore, if we were to substitute lambda and mu both into the vector PQ, we would get that PQ is the vector minus 0.5, minus 1, minus 0.5. The magnitude of PQ, therefore, will be the distance between the two lines at their closest point. The magnitude of PQ is root 6 over 2. So that is the shortest distance between the two skew lines. Now pause the slide and repeat the same process using these two lines. So here we have two lines with point P on one line, point Q on the other. We know that P to Q is perpendicular to both of the two lines. So OP, because we know that P lies on the first line, we can write OP as 1 plus lambda minus lambda 2 plus lambda. And because we know that Q lies on the second line, we can write Q as 0 plus 2 mu, 11 plus 0 mu, then 0 minus mu. So from this, we can find an expression for the vector PQ. This is OQ minus OP, which is 2 mu 11 minus mu minus 1 plus lambda minus lambda 2 plus lambda. So PQ is 2 mu minus 1 minus lambda, 11 minus minus lambda, so 11 plus lambda, and then minus mu minus 2 minus lambda. So we know that PQ is perpendicular to each of the two lines, so we're going to find the scalar product of PQ with each of the two direction vectors. So for the first line, the direction vector is 1 minus 1, 1. Find the scalar product with PQ. We get 2 mu minus 1 minus lambda, 11 plus lambda, minus mu, minus 2, minus lambda, and we know that this has to equal 0. So multiplying this out gives us 1 times 2 mu minus 1 minus lambda, minus 1 times 11 plus lambda, plus 1 times minus mu minus 2 minus lambda. So to simplify this down, 2 mu minus 1 minus lambda minus 11 minus lambda minus mu minus 2 minus lambda equals 0. So this gives us minus 3 lambda plus mu minus 14 equals 0. Okay, if we now find the scalar product of the second direction vector with vector PQ, we get 2 mu minus 1 minus lambda, 11 plus lambda, minus mu minus 2 minus lambda. Again, that will equal 0. So this expands to give us 2 times 2 mu minus 1 minus lambda plus 0 for the middle component, minus 1 times minus mu minus 2 minus lambda. So this expands to give us 4 mu minus 2 minus 2 lambda plus mu plus 2 plus lambda equals 0. So this simplifies to give us 5 mu minus lambda equals 0. Solving these two simultaneous equations leads us to lambda equals negative 5 mu equals -1. From this, we can calculate the vector from P to Q by substituting in these values. So we get 2, 6, 4 for PQ. Therefore, the magnitude of PQ is √56 or 2√14. The shortest distance is 2√14. Now complete the final two questions on exercise 9D, that's questions 16 and 18, and also the mixed exercise on page 220 to 222.